All right, so I'm going to go ahead and start now. It's 30 seconds late. I hope you'll forgive me. I know, that was like the lamest joke ever, wasn't it? Thank you for laughing. So, hi and welcome to Machine Learning for Gamers, Dungeon Forecasts and Dragon Regressions. So, real quick survey of the audience. How many of you feel like you know anything about machine learning? A few of you? Okay. So if you feel like you know a little bit about machine learning, well, we're going to talk a little bit about machine learning. How many feel like you've got a lot of expertise in machine learning? Good. You would be bored. So this is intended to be sort of an intro talk to some of the things you can do with machine learning. It's not actually, there's no code. We're going to talk about the types of things you can do with machine learning. Another quick survey. How many of you have played Dungeons and Dragons? Thank God. I gave this talk, the first time ever I gave this talk was like to a engineering fraternity at a university in California. And there was like 13 people that showed up, and 11 of them were not programmers. And none of them had played Dungeons and Dragons. I blew through my slides in like 20 minutes. It was awful. So, okay, well, another question. 5th edition, Pathfinder. Okay, you guys can get out. Okay, so my name is Guy Royse. I know the sign out there says that my name is Guy Rose. I assure you they are wrong. I am Guy Royse. I'm not Guy Royse. Some people make that mistake sometimes. And I'm a developer evangelist with Nexosis. And there's my Twitter account, so you can make fun of me while I talk. There's my email address, so you can continue to make fun of me after I'm done talking. And I work for a company called Nexosis. And you probably haven't heard of Nexosis. Who has? Anyone? A couple of you. So probably because I talked to you yesterday. So Nexosis is well, I'll read the slide here. This is the only slide I'll read. Is a company of developers focused on providing easy access to machine learning. So we've got an API, which I'm not going to talk about today, that is an automated machine learning platform. So you can upload your data, ask a question, say this is my target, these are my features, which I will explain, and then it'll run all the algorithms and pick the algorithm that built the best model. So it's targeting developers who don't want to get deep into machine learning. And in building this product and talking about it to people, I quickly realized that a lot of people were approaching machine learning the way they approached all the other technical things they've learned in their career. So, you know, maybe you are a C# developer and you're deciding to learn Python. Well, you know what Python's for, right? It's a programming language. It's for writing programs. And you're trying to build a web app, and so you're using something like maybe Django or Flask, depending on whether you want to do, you know, I picked like the opposite extremes, didn't I? But, and so you know what all those things are for, you just need to know how they work. And so as developers in our career, as we learn new things, it's all about the how. And what happens is people try to do that for machine learning, and it's not like the other things, and it doesn't work. And so you go on to Stack Overflow, and people are asking all these clueless questions, and then everyone's downvoting their answers, and it's a giant dumpster fire. Some people feel that Stack Overflow looks like that a lot anyhow, but I don't want to diss Stack Overflow too much. It's actually a great site. I get all my code from there. So what I found in telling people about this was it felt a little bit like we were selling instant coffee, but no one knew what coffee was for. And so I thought, we need a slide, we need a presentation to explain what coffee's for. So that's what this presentation is. And you know, what better analogy to use than Dungeons and Dragons, right? You know, can't go wrong with that. So before we get too deep into it though, I do want to add one really important qualification. Anyone know what this stands for? Yes, sir. I am not a data scientist. I have spent the last 25 years writing software. I'm not even particularly very mathy. And it turns out, you don't have to be a programmer, right? So you're all programmers, right? Most of you, developers. When was the last time you used anything more complicated than basic algebra? Honestly, right? I mean, who was president? I mean, it's probably been decades, right? Well, for some of you, for me, I haven't used anything beyond maybe some basic algebra my entire career. And because a lot of what we do is about moving data from point to point, doing some basic math. And so I don't have those skills. And a lot of you guys don't either, I'm sure. You guys have probably taken more math than I have if you've got a computer science degree, because I don't have a computer science degree. And so I haven't had calculus or anything like that. I hear that it's used to solve problems of some sort, but you know, I'm still trying to stick it to my math teacher back in high school. I'm not going to need this when I grow up, which is not true. But actually, I kind of wish I had that math now because it would make my job a lot easier. But I am not a data scientist. So if you've got deep questions about algorithms or specific like bucketing techniques and when you do this with a decision tree and blah, 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 I can't answer those questions, so please don't ask them. I will write them down, and I will take them to my friendly data scientist, and she will answer it for me, and then I will email you back. So that's the contract, I guarantee. But I'm not a data scientist. And this is not a deep data science talk. So I think machine learning is kind of like Dungeons and Dragons, right? It's got some parallels. People are really, really excited about it. I mean, you get someone that's in machine learning, they can't stop talking about it. You get someone that plays Dungeons and Dragons, you can't get them to stop telling you about their character or that adventure, even though you don't want to hear it. They're going to tell you anyhow. It's got all this weird jargon that you're not familiar with. All these terms, you know, what is regression? What is classification? In Dungeons and Dragons, you've got, you know, hit dice and armor class and stuff like that. And it's got all these weird tools that you've never seen before. I mean, look at all these dice. If you had not played Dungeons and Dragons, you would look at that and say, what the hell? Look at what we got up there. We got some square dice that look like regular dice, but pretty sure one of those has rock, paper, scissors, lizard, Spock on it, because that comes up in D&D all the time. We've got some, it looks like some treasure dice there. We got a 20-sider there in the middle. We've got this thing that looks like a top that's got numbers on it. It's like a roulette wheel or something like that. It's just all confusing, but everyone's excited. And so that's kind of how I'm relating to machine learning here. So what is machine learning? Bonus points if anyone can tell me what this is a picture of, by the way. Anyone? Yes, it's Babbage's difference engine. A very old machine. I thought it looked cool and steampunky. So, so I like to think that machine learning is, it's kind of like it's math at scale. So part of why everyone's been getting excited about machine learning lately is because we finally got enough transistors to run math problems that we've known how to do for a long time, but we can't actually scale them up. You know, because every single time you add that column, it doesn't just grow linearly. So if you got 50 columns of data that you're using to predict something, that's computationally intensive with basic statistics. But we can ramp that basic statistics up to really high levels that we haven't been able to before. So I like to think of it as math at scale. I also like to think about it as kind of like learning from example. So when you program something, you've got this, you know, it's very prescriptive. You tell it exactly what to do. You've got the formula in there, you do it. And it's formulaic. But machine learning is, you sort of upload a bunch of examples, and then it can find things that it hasn't seen before. And that's kind of how humans learn. And the examples I'll get to will make this a little clearer here in a bit. But humans kind of, like, look at houses. Housing is always a great example for machine learning. If you're trying to figure out how much a house is worth in a neighborhood, if you're, like, say you want to sell your house, and you're trying to figure out how much you should list it for, you look around your neighborhood, you look at some features of that house, the square footage, the lot size, what year it was built, and houses in the neighborhood, and all those features of those houses, and you come up with a guess as to how much that house should be worth. And that's kind of what machine learning does. It's learning from examples. There's a phenomenon in machine learning called overfitting, which I don't have a slide for, but I'm going to talk about briefly, which is where it, in essence, memorizes all the examples, as opposed to figuring out the pattern of the examples, the shape of that curve. Instead of getting the shape of the curve, the generalized shape, it's getting real specific and it just memorizes all the answers. And people can do that too. I'm sure we all got through college by memorizing many answers without understanding anything. So machine learning is about understanding, not memorizing. There's actually a tool for getting a very precise memorized answers out of a computer, and it's called a database. That's not what we're building here. So at its simplest, machine learning has got three basic steps. You're gathering your data, and you're prepping it, you're cleaning it. You're getting rid of outliers, you're figuring out what are your features and what are your targets. Then you use that data to build a model. And then once you have that model, you can use it to make predictions. So thanks for coming. So when we're gathering data, we got some stuff about gathering data. We've got a target and we've got features. Sometimes they're called dependent and independent variables if that person has a math background. We've got some encoding. Sometimes your data isn't a number, and so you need to encode it in some fashion. And you've got this idea of imputation where you need to fill in the blanks. So target and feature is actually really easy. These words confuse things, but the target's just the thing you want to predict. And the feature is things that affect the thing you want to predict. And that's really it. If I go back to the housing example, the target would be how much is the house worth? The features are the square footage of the house and the lot size and the year it was built and stuff like that. Whether it has a basement, how many bedrooms and bathrooms it has. You can come up with lots of features for houses. And that's all there is really for targets and features. Encoding is taking non-numeric data and turning it into a number in some fashion. So you've got two types of data. You've got categorical data and quantitative data. Categorical is it this or that? Is it a hot dog or a wiener dog, right? It's a class. It's a category. It's an enum. An enum is a good way to think about it for a developer. Whereas numeric data is, well, it's a number. We know what numbers are. And so encoding is that process of taking those categorical things and making them into some sort of numeric representation that we can operate against. Imputation is the process of taking nulls in our data and turning them into some meaningful default. So if you've got like the housing data example, you need to figure out, say the lot size isn't there, but you want to use it as an example anyhow, then you might look at all the other lot sizes and take the average. Or, depending on what you're doing, you might default it to 0. Depends on what makes sense. Like if you're trying to guess what the sales amount was, and you don't have any data for that time period, 0 is probably a reasonable assumption. If I didn't record that I sold anything, I didn't sell anything. Any questions so far? So here's a couple simple examples of encoding. So turning a Boolean into a number is probably the easiest thing in the world. I probably don't even really need that on the slide there. But it gave me an excuse to use the word goblinoid on a slide for a presentation. So is this character a goblinoid or not? Are they a bugbear, a goblin, a hobgoblin, one of those psionic blue goblins, for those who are really, really into D&D? So in here, a yes is a 1 and a no is a 0. Surprise! We know that, right? We've been doing that for years. But the color of a dragon's a little more interesting because it's taking something categorical and turning it into numbers. And so what we're doing here is you've got your black, blue, green, red, and white dragons, all the evil ones, because they're more metal. And for each value that's in that column, each category, you create a new column, and then you put a 1 in the one where it matches and a 0 in the ones where it don't. So you see here, if you look, that for a black dragon, you got a 1 in the black column and a 0 in the rest. And for the blue dragon, you got a 1 in the blue column and a 0 for the rest. This is a technique called one-hot encoding, and you put the 1 in the column that's hot. That's why it's called one-hot encoding. I guess the other ones are cold. It's kind of like that warmer, colder game we used to play when we were kids. Maybe we play with our kids still. My GPS works that way, by the way. It just says you're getting warmer, you're getting colder. I totally stole that from XKCD. So once you've got your data into a form that's useful, you've encoded stuff, you've imputed values that are missing, you've selected your features, you've selected your target, then it's time to build a model. And so to build a model, you have to pick an algorithm, and there are lots to choose from, and they do different things depending on what you're trying to do. And then you have to select your train data and your test data. So you're going to take a portion of your data and set it aside for training the model. And you're going to take the rest of it and set it aside for testing the model. And you can actually, I've seen some people will take a even bigger, another portion of the data set aside to hold it back because they're paranoid about overfitting. There's more decisions to be made here than just train and test, but lots of times it's just 80% of it's train data, 20% of it's test data. And so the way that's going to work is when you build your model, it's going to take that train data and, well, it's going to train the model. And then when it's done doing that, it's going to compare it against the test data and measure how accurate, measure what the error rate is on that model. And so you don't want to have this data overlap, because then if you just used all of your data, if you used 100% of your rows to train your model, then your model, you have no way of verifying that it's good or not, because you're going to tell it things it knows already. You want to tell it things it doesn't know and see if it finds that general shape of that curve. So here's some algorithms. There's lots of them. I honestly only know what a few of these do. These are just some of the ones that, I took them off of Nexosys' website. Their algorithms our API uses. And so I know what a few of these are. I mean, I know what decision trees are. I know what statistical regression models are, that kind of stuff. But you pick an algorithm. Then you've got data, and it's just rows and columns of data here. So a lot of times when people think about machine learning, they're thinking about deep learning, or they're thinking about artificial intelligence. Deep learning is about neural networks, and it's being used a lot by like Google and other big tech companies to like identify things in images. Is that a stop sign or not? Is that a cat or a dog? Those sorts of things. Those are much harder problems, and it's called deep learning because there's lots of layers in that neural network. So this isn't deep learning type stuff. This is a little more mundane machine learning, shall we say. We're just dealing with rows and columns of data. It's like something you pull out of a SQL database. And so here we would randomly select some training data, and you'd randomly select some test data, and then you'd go to town. And when you're done with this process of picking an algorithm and building a model and doing your training and testing and all that kind of stuff, what you're going to find is that your model sucks. And so you're going to go back and you're going to look at your data. And you're going to say, well, some of these records I have are really outliers, and they're throwing it off. So let's get rid of the outliers. And actually, it turns out this column, this feature that I thought was really important, it isn't important at all. So let's take that out. It's creating a distraction. Or this feature here is way too strong. So for example, sometimes you can pick a feature that's actually a component of the thing you're predicting. So if I was trying to predict, say, the power output of a windmill, and one of my columns was the voltage going to the windmill at any given time, and another one of my features was the amperage going to the windmill, then those are the ones, there's a formula for that, right? Those are going to be, they're going to skew your model. They're going to throw it off and make it not accurate. So you figure that out. You take those columns out, you take those features out that you don't want, you tweak it, you run it again, and it sucks a little less. And then you realize, well, maybe this other algorithm would be better, and so you switch your algorithm out, and you go through this loop several times until you have something that you're satisfied with. And satisfied can mean a lot of different things depending on what you're doing. If, as I show you here, we're trying to predict the value of a dragon's treasure hoard in gold pieces, then a 20% error rate is probably acceptable. If you're trying to determine whether that's cancer or not, 1% is not acceptable. Right? That's 1 out of 100 people. That's a big deal. And so depending on what you're doing, it makes a big difference as to what is an acceptable error rate. And and smaller is not better. So if your error rate is really small, that could just mean that your model's overfit, that it's actually bouncing around to hitting all the data points as opposed to finding the shape of that curve. Once you've got a model, you can use it to make predictions. And that's pretty much just a matter of providing the features, and then you get your target. I mean, that's the end game. And so if you were writing a function to wrap up all your machine learning stuff in your application, you would have a function that says predict, dragon's horde value, and it would take the features as arguments and would return the prediction. That's all we're doing here. So I'm going to talk about 5 types of machine learning problems, things that you can solve with machine learning. And I'm going to give some examples. And those 5 are regression, classification, anomaly detection, forecasting, and impact analysis. I may have had clustering in the abstract as well. I can't remember. I've taken that out for a lot of conferences, but I might have missed this one. But clustering is another one. I don't have any slides on it. I may talk about it briefly. And you remember when you were in school and they said you should have a slide that tells you what you're going to tell you? And say what you're going to say, then say it, and then say what you said. Yeah, this is the one where I say what I'm going to say. So let's start with regression. And so what we're going to do here is we're going to determine the value of a dragon's horde in gold pieces based on the age, color, and hit points of that dragon. So a little bit about dragons if you aren't familiar. Dragons have an age. They can be a wormling, they can be young, they can be an adult, they can be ancient. And that's a useful feature because the older a dragon, the more time it's had to accumulate gold. And probably the more powerful it's become. So the easier it is for it to accumulate gold. The color of the dragon is, on the left here we've got black, blue, green, red, and white. Those are the evil dragons. And on the right, you've got brass, bronze, copper, gold, and silver. Those are the good dragons. And the color of the dragon says a lot about the dragon, in addition to whether it's good or evil. A good dragon is probably not going to have as much gold as an evil dragon because the evil dragon just goes and takes it. And the different colors of dragons, some are more powerful than others. So a red dragon is very badass, whereas a white dragon is kind of stupid. So the red dragon's probably going to have more gold. And so this is an important feature. Hit points, how much damage can the dragon take until it dies? If a dragon is harder to kill, it's probably going to be able to live longer and accumulate more gold. And the adventurers that come to it and try and kill it, well, they're going to leave their gold behind too. So this is going to drive up the gold piece value of their horde. And then you've got their horde. That's just the total value of all their treasure. So some sample training data might look something like this. You would have way more than the 15 odd rows that I have on here. You'd probably have thousands of rows, maybe. Maybe tens of thousands. It really depends on how many features you have, because you got to hit a lot of more permutations. But this is just that, you get age, color, hit points, and horde value. I actually rolled the horde values randomly at work. And so I got to take my dice and Dungeons & Dragons books to work and rolling dice, figuring out how much the dragon's horde's worth. It was so much fun. Actually, I didn't take my books. I downloaded the PDFs off the internet. I took my books in, sorry. I totally wouldn't steal intellectual property. But I do own all the books. So here is us selecting then at random some training data. Here's some test data. And then we'll have a model. So once we have that model, what does it look like to ask a question of it? Well, we could actually build 2 different models with this data. We could build one model, which is predicting horde value, which is the problem I postulated to you. And so we would provide the age and the color and the hit points. And then the horde value would be what we get back. We could, however, build a model that we want to predict the hit points instead. The idea being that maybe gold influences how many hit points a dragon has. And so we could build this model as well. So we'd predict either of these values. It'd be 2 separate models. And you just provide the features, and you get that big pink question mark there. It gets the answer for you. That's how it would work. That's the problem it solves. And so you might be looking at this and thinking, can I predict the color of a dragon? Could I predict the age of a dragon? Not in years, but in categories. The answer is no. Well, the answer is yes, but not with regression. See, the age and the color are categorical data. They're categories, like I talked about earlier. Whereas hit points and horde value, they're quantitative. They're numbers. And regression predicts numbers. But there's another machine learning technique that predicts categories, and that is called classification. So, classification is figuring out what category a thing belongs into based on a bunch of examples. It's the same basic idea as regression, except it's predicting a category. And in this case, we're going to do what I like to call literal classification. Because we're going to take 6 key ability scores: strength, dexterity, constitution, intelligence, wisdom, and charisma. We're going to take the race you want to play, whether it's a half orc or half elf or human or whatever, and we're going to determine what class you should play. It should be a fighter or a barbarian or whatever. So it's the best classification example I could ever think of. Literal classification. So here we go. Here's our abilities. I mentioned them earlier. They typically have a value between 3 and 18, so very much a number. You've got your race. I got these all from 5th edition. Personally, I don't like Tieflings and Dragonborn because they're tacked on. They feel tacked on in 5th edition. I played D&D back in the 80s, and we didn't have those. And so all my really old campaign worlds, I have to shoehorn them in. I got to retcon them in after the fact, and so I just kind of wish the Tieflings and Dragonborns would go away. Any fans of Tieflings and Dragonborns here now that I've totally dissed them? You would, right? But race determines a lot about your abilities. So one of the key things you get out of race in Dungeons and Dragons is you'll get boosts to your abilities, and you'll get special abilities that work well with certain classes. So elves are quick but frail. Dwarves have a high constitution. Half-orcs are really strong but not really very bright. That kind of stuff. And then you get your classes, which is the thing we want to predict. Do I want to be a barbarian with the big sword or the big battle axe coming running in? And so, barbarians, half-orcs tend to make good barbarians, so half-orc is significant for that. Whereas elves, probably not the best barbarian. So what we've got here is a bunch of data of sample characters that are good options. So characters that have these abilities and this race tend to play this class. It would be effective. And so you get a bunch of data that explains all this. You upload your model, you select your test terrain, you upload your data, you train, you test, you get a model. And then when you go to use it, it looks like this. Now there's actually a couple different algorithms. If you use just like say a straight up decision tree to do this classification, then you're going to get just an answer. With these stats and you want to be a half orc, you should play a barbarian. But there are other algorithms that you can use that will create a forest of decision trees and give you a score as to which one works best. And so I actually like that better. I feel like it gives you more of a sense of confidence about it. So you can see here, for example, the barbarian's got a 0.97, but the bard and cleric are, they're close second and third. So it gives you a little more information than you had if you just said you should play a barbarian. And I think that's useful. Now, before anyone looks at that and says, with a wisdom of 9, that's a terrible stat for a cleric, I will say that these numbers are bullshit. I just made them up. They're just numbers. There's also a temptation to look at those scores and think that they're percentages. How many thought they were percentages? Yep, I tricked you. They're not percentages, they're just a score. They're only meaningful in the context of themselves. So they're only, if you built another model and got different scores, you could not compare them against each other. If you built another model with exactly the same features and the same target, but a different data set, you couldn't compare them to each other. They're only meaningful in the context of a given model. You could also, of course, build a model that predicts class or race based on the class you want to play. So if you want to play a cleric with these stats, I should probably be a dwarf or whatever. Good so far? How am I doing on time? Okay. So we're on to the third out of 5. we're on anomaly detection. And so anomaly detection is all about finding outliers in your data. And it's a type of learning that's called unsupervised learning. So the previous two ones, classification and regression, are supervised learning. We know the answer in our examples. So we provide a bunch of examples and we say this is the answer. And then it learns the types of scenarios that might match a given answer. In unsupervised learning, we don't know the answers, we just have data. And anomaly detection finds outliers. Clustering is another type of unsupervised learning, which is like classification when you don't know the categories. It just finds logical groups in your data. It's kind of analogous to sorting out your junk drawer and saying, well, this is a paperclip thing, and you sort of sort it out and start making piles as it makes sense. Anomaly detection isn't like that. You're just picking the weird stuff out. And so what we have here is find the atypical characters. Determine if a character is atypical or not based on a bunch of characters that have just been a bunch of existing characters. Is this character an outlier or not? And it'd be tempting to say, is this a good character or a bad character? You know, is this a playable character or not playable character? But if you know in your data that you're uploading whether the character is playable or not, then you've got a classification problem. You don't have an anomaly detection problem. And so lots of times you think you have an anomaly detection, you want to find a character that's of a certain type. Well, that's actually a classification problem. So here's the same data that we've been using. The abilities, the race, the class. And if we run it through an anomaly detection algorithm, it will give us a score that will show us how anomalous, how much of an outlier. In our case, I'm going to say the typicality. Is that a word? It is now. Of that character. And again, this is a score, just like with classification. It's only meaningful in the context of this model that you've built from this sample data. And so you get this score, this column back that shows you which ones are outliers and which ones aren't. And so negative in this case is more of an outlier, positive is less of an outlier. And once you've built a model using this, you can give it new data and get that score. So I'm putting up two more barbarians here. What's that score? And then again, that score is meaningful in the context of the other scores. So you can find anomalous data, outlier data in a pile of data that you have already, but you can also then use that as a basis for looking at other data. So a practical example of this might be looking at like CPU metrics. So you've got like CPU utilization, free memory, all those things that you can get on a server. And if you get enough of those over time, you can find ones that are, you can run those out and build an anomaly run them through anomaly detection and find the ones that are outliers. And then you could continue to feed new ones into that model and get additional outliers and say, this server, I should look at it because it's weird. Where these ones are humming along like they usually do, assuming your usuallys are good. And so that's anomaly detection. So forecasting. Now I've got another example of forecasting that I use with Bigfoot data that's particularly funny. I've got a data set of 4,500 Bigfoot sightings. And I wanted to predict how many future Bigfoot sightings we were going to have based on historical Bigfoot sightings. And so I was on Quora one day, and someone said, what's a really strange thing that you or someone you know has used machine learning for? And so, you know, it's like, oh, well, I used it to predict how many Bigfoot sightings there are. And I also used impact analysis to determine the impact of the X-Files on the number of Bigfoot sightings in the 90s. Did it go up because of the X-Files? Which seemed like a pretty plausible hypothesis. And he came back at me and said, but that's not machine learning, that's just statistical analysis. And I'm like, oh, I suppose. And before I got a chance to respond to the guy, someone piped up and said, software engineers discovered math and called it machine learning. And so forecasting and impact analysis, the next two, fall into that category of math that we're calling machine learning. And forecasting is about looking at historical data and predicting future data. In this case, what we're going to predict is the number of encounters that will be completed by my gaming group at our weekly gaming session. So how many of you here who play D&D run a game? Right? And how often do you over-prepare material for that game? All the time? Because you're afraid you might run out? How often do you under-prepare? Right? It'd be nice if you had a good idea, if you could predict, if you could forecast how many encounters your party will get through based on information about your players. And so that's what this is. And I'm going to turn this into an app. I'm going to code it up. I think I'm going to live stream it while I code it. Because there's actually a lot of useful data here. So we've got the date when our session's happening. Dates are neat for time series data, like for forecasting and impact analysis. Because with dates, you've got all kinds of hidden data in there, right? It's a date, but it has the day of the week. Like, that's sort of a category. Fridays are different than Mondays. If you're predicting, pizza buying trends, it tends to go up over the weekends. The hour of the day is significant, depending on what you want to forecast. Even the minute within the hour can matter. The day of the year, the month of the year, these are all things that are embedded in a date. They're features that that date fans out to have a lot of features that affect your model. And so in this case, we're doing weekly sessions, so it's the week. And so certain days are going to be, certain weeks are going to have different characteristics. The week of Christmas is very different than, the week of Valentine's Day or this week, right? Players, these are all the players who attend your game, and whether they're there or not. You've got how much time you spent playing the game, and you've got the thing you want to predict, how many encounters you have gotten through or wish to get through or expect to go through. So here's our data. So I selected, I assumed we had 4 players here: Alice, Bob, Chuck, and Eve. Alice and Bob are often used for that InfoSec example users, but through a wonderful coincidence, it also happens to be the names of my grandparents. So it always makes me a little warm. So we got our date, we got whether Alice or Bob or Chuck or Eve were there. We have how long our session was and how many encounters we got through. And so you can imagine how different players might impact, their attendance or not, lack of attendance would impact the number of encounters you get through, because if you got less people, maybe the combat gets drug out, but maybe it doesn't if you got more people. Maybe Bob talks too much. Maybe Chuck is the ever noob and still doesn't know the rules. Right? There's a lot of dynamics happening there. So having those as columns, as features in your data set are very useful. Length of your session, obviously, longer session, you're going to get more done, right? And then the number of encounters is, I'm thinking encounters in terms of, we went into the dungeon and we dealt with the animated statue that was guarding the entrance to the dungeon. And once we got past that, we got into the hall that had all the skeletons in it, and we defeated them, and we got behind them, and then we found the goblins that had come up from the Underdark, and we're fighting those goblins. And so we got through that, and so that was 3 encounters done, right? So you could use this to make predictions. Note the date. So the last date on here is February 5th, 2017. So then what we can do is for future weeks, we can say, well, Alice, Bob, Chuck, and Eve, this is their schedule. And we know that on the 26th of February, Eve's not going to be here, so we'll put a no in there. And then we got the, everyone else is planning on being there. And we know that on the 12th and the 19th, we're going to play for our typical 4 hours. But on the 26th, we're going to start a little bit early, and so we're going to play for 6 hours. So given all that historical stuff back here, what will the future look like? That's incredibly useful. You could also ask the length. Say, so this is an interesting way of looking at it. I want to get through 5 encounters on the 19th, and these people are going to be here. How long of a session do I need to run? That's useful. I want to move that story forward for my D&D game forward at a certain rate. And it demands 5 encounters. So we're going to do whatever it takes to get that. So we'll schedule accordingly. And that's forecasting. It's predicting the future. Now, it's worth noting that the features that affect past values for forecasting have to be features that are knowable in the future, right? We can, or at least be reasonably knowable. So we can be reasonably sure that Alice, Bob, Chuck, and Eve's attendance is going to look like this. Now, we may get a surprise. That happens. But we have a reasonable assurance. We know that we're going to schedule how much time on the calendar. So we've got a reasonable assurance of that as well. So we can use that to make predictions. But if we had no way of knowing how long we were going to game, then we couldn't use that as a feature. If it was just something we couldn't know. If you use, say, weather as a feature, the temperature and the rainfall, and you're trying to predict things 6 months out, that might be a little harder to get. And so that's not necessarily a great feature for forecasting because you'd have to know the weather. So impact analysis is kind of like forecasting, but it happens in the past. And in here, we're going to measure the impact of taking our game from Pathfinder to 5th edition. And so that's why I asked everyone if they preferred 5th edition and told everyone else to get out, because we're upgrading. Out with the old, in with the new. So, you know, we've switched our game from Pathfinder to 5th edition, and we want to see, did that increase the number of encounters we got through, or decrease the number of encounters we got through at a given session? Did it speed up our game or not? And that's what impact analysis does. I like to call it beforecasting. So you're making a forecast in the past. So you've got this historical data, and so here's our historical data. It's the same data I had in the previous slide. But I know that on January 1st, as part of a New Year's resolution, I switched the game to Pathfinder, or from Pathfinder to 5th edition. But the model doesn't know that. It's blissfully ignorant. And so I can ask the model and say, based on everything in 2016 and back, what do you predict January 1st through February 5th, how many encounters should we have gotten through? And then compare that against what we actually got through. That'll give me a sense of the impact of that event. Because the model is going to make that prediction based on all that past activity and not on the future activity, or the period that we want to do the impact analysis on. And so this looks a little clearer when we look at this slide here. So on the top here, we have the date, you know, January 1st through February 5th. On the bottom, we have that same date, and we're saying what would have happened based on the past. And so we're filling in those pink question marks again. Now, we know what actually happened. That's up top. But what we can do is we can get that prediction, and we can compare them. And so here is our actual encounters. So on January 1st, because who doesn't play D&D with a hangover? We got through 3 encounters, but the model predicted that we get through 5.0346 encounters. And so the model predicted more than we actually did. And on the 8th and the same, it's consistently higher than what we predicted. And so then you can look at the difference here and say, well, we actually are 2 in the hole. We got through less. I probably should have made those numbers negative in the change column there. So our predicted encounters were 5. We actually got through 3. Our predicted encounters were 8. We actually got through 5. And so what that means is the impact of switching from Pathfinder to 5th edition was to slow down our game. So my hypothesis is false. Long live Pathfinder. So this is the slide where I tell you what I told you. We've covered regression, classification, anomaly detection, forecasting, and impact analysis. I mentioned at the beginning that I work for Nexosis. We have an API. It's free. It will do all of these problems I talked about today. So you can do all those types of machine learning with our API. And if you like the talk or if you think this is useful, go check it out. The community edition's free. It's just throttled by use. You can only do like 10,000 predictions a month or something like that. Still a lot. So go check it out. It helps us out. I appreciate it. And questions? Your stunned silence is very reassuring. Yes, sir. So the question is how do I take the literal classification and turn it into something useful? Is it a recommendation engine? Is it a, what was the other thing you said? Or to guess which class you should be playing? I personally was kind of envisioning it as a recommendation engine. So you could go in there and, you know, based on all these example characters, here's a list of characters you should play and how they score against each other so that you can pick one that would be suitable based on your abilities. So I was kind of imagining it more as a recommendation engine. And you know, honestly, you could totally build a web app that does that, right? That wouldn't be a challenge at all. You just need a bunch of really good example characters. The data is always the hard part, right? So does that answer your question? Good. Any other questions? Okay. Well, I think you're going to get about 14 minutes of your day back. I apologize for going a little short here. My name again is Guy Royse, not Guy Rose. And if you want to reach out to me, there's my contact information. And there's credits for all the awesome images I used. And there's my company's logo. Thanks for coming.